Hello everyone, thanks for stopping in. Today we're going to be talking about Math 121, section 3.2, and this deals with measures of variation. And I wanted to start off with a disclaimer that the concept of variation can be a difficult one. The important thing is to make sure you understand what you are doing, and you're not just blindly calculating numbers. Make sure you understand why we care about these numbers. Because an important characteristic of all measures of variation we study is the smaller the number, the less varied the data is. If you have a smaller measure of variation, your data is less spread out. Now, in the real world, an important and sometimes quite difficult goal of businesses and industries is to reduce variation as much as possible. Think about it. When you buy a calculator, you want it to work correctly every time. You don't want any variation in the answers, right? When I type 5 times 7, it should always give me 35. There should never be variation, right? Now, in other examples, that might not be as easy to control as with a calculator, right? There might be more difficulties with variation. Think about like a textbook. When this comes off the assembly line, the glue might not have been as nice, or maybe there's some wrinkles in the pages. There might be variation. Machines aren't perfect, right? When things are made, there is sometimes variation in the products, but we want to reduce it as much as possible. Now, it should be noted that if you're comparing different data sets, you can't compare most measures of variation directly. If we look below, we have the first measure is range. If I know the range for one data set about salaries, and I want to talk about the range for heights of students, those aren't measuring the same thing. I cannot compare those numbers. So I need to make sure that my numbers come from the same data set when I want to compare them. That's our little bit of disclaimer to start. Let's dive into the notes. Let's take a look here. We've got some rounding rules for measures of variation. Well, the rounding rules are we round our measures to one additional decimal place. We always carry one extra decimal place, right? That's the same rule as for measures of center. We round to one extra decimal place. So if our data was all whole numbers, our answers will have one decimal place. If our data had 3 decimal places on the end of them, our answer would have 4, always one more decimal than the original data. Now, let's take a look at our first determination, and that's the range. The range is the difference between, I abbreviated between, the maximum and minimum data values. Data values. The range is the difference between the max and the min. It's how much range does the data take up. The formula is quite easy. It's range equals max minus min. You just subtract the max number minus the minimum number. Take the biggest, subtract the smallest. It's got some properties. It is not resistant. Not resistant. Outliers have a massive effect on the range, right? If my maximum number is an outlier, that drastically changes my range. Same if the minimum number is an outlier. That drastically changes our range. Also, it does not really reflect the true variation. Does not reflect the true variation. And let's think about that for a second. Let's say on the first exam, one student got a 100 and one student got a 25, and every other student got a 93. One student got a 100, one student got a 25, and every student got a 93 besides them. That data is not very varied, right? Almost everybody got a 93, except 2 students, the max and the min. The range would say it's got a spread of 75 points, right? Max 100, min 25, a spread of 75. That is not very helpful for that data set. So the range isn't necessarily the best measure of variation. It's just one calculation we can do, and it gives us an idea of how spread the endpoints of the data are, right? It gives an idea of how spread out the data is overall from end to end, right? So let's take a look at an example. Consider the following set of sample data taken from a stats class and pertaining to student exam scores. Let's see, I've got some exam scores here. Calculate the range. Range equals, well, what's the biggest number here? It looks like 94, right? 94 minus, let's see, 57, that looks like the smallest, right? 57 for the min. Let's see, that'd be, 37, right? Let's double check. Always good to double check with our calculator, right? 94 minus 57 is indeed 37, right? So the range is 37. Nice, easy, short, and sweet, right? Range is nice and easy to calculate. We can calculate the range quite easily. It's just subtraction, right? Now, the second measure of center, which is the most important thing we are going to talk about so far in our course as far as calculations go, and that is the standard deviation. This is a really important concept. So make sure you are understanding the standard deviation. This is something you want to make sure you focus on. So the standard deviation is a measure of how much the data is varied from the mean. The standard deviation compares the data to the mean. It compares the data to the average. It tells you how spread out is the data from the average. Sometimes data might be really clustered around the mean. It might be really centered on the mean, or it might be more spread out and more varied, right? That's what the standard deviation can tell us. How clumped around the mean is our data. It compares the data with the mean. We have some notations. We have two different notations. Lowercase s is the sample standard deviation. I'm going to write standard dev. And then sigma, the Greek letter sigma, a circle, an O with a little line off of it, right? The sigma is the population standard deviation. So sample and population have different letters. This is sigma. Sigma. S and sigma. Once again, the Greek letter is for population. The English letter is for sample, right? So we have Greek letters and English letters again, right? Greek letters for population, English letters for sample. Now, we actually have two formulas for standard deviation. So let's look at the formulas. The first is S is equal to the square root of the sum, and then in parentheses I have x minus x bar squared over, and in the bottom I have n minus 1. That is the sample standard deviation. Whereas the population, let's look at that formula and then talk about the differences, is the square root of the sum of x minus mu squared over big N. So the sample is the square root, and then we have the sum of x minus x bar. X bar is for sample, right? This is the mean, and we square those, and then little n, that's the size of the sample, right? And we subtract 1 from it. So the sample and population have a different form. Look in the population. It's x minus mu. That's the mean, right? So the top is the same, right? The top is the same. I'm just using the different symbols. The bottom, though, I have n minus 1 and just n. The population has big N in the bottom. The sample has little n minus 1 in the bottom. So make sure you recognize those differences. Now, we actually won't be using the formulas necessarily to calculate standard deviation. We're going to come up with a better technique for it. But first, let's get some properties. The first property is standard deviation. Standard dev is never, it is never negative. And 0 only if all data is the same. So it's almost always a positive number. It's never negative. It can never be negative. It can be 0 if and only if all of your data is the same number. Let's say I gave a quiz and every student got 100 on it. Then the standard deviation would be 0. It can never be negative though. So if you calculate a standard deviation and you get a negative number, you know you messed up. It cannot be your answer. It can never be negative. It has to be positive. Always positive. And 0 only when all your data values are the same number. Next, larger standard dev means more variation. Let's say I want to measure the heights of 2 different football teams. And I'm measuring height, and I'm measuring football teams. I have 2 different data sets. Maybe I measure the local high school football team, and maybe I measure the Super Bowl champs from last year. I actually don't know who won the Super Bowl. It doesn't matter. And I measure each team, right? The Super Bowl champs and the high school team. And I notice that the Super Bowl champ team has a larger standard deviation. That means their heights are more varied. They have more variation in their heights. Because the larger standard deviation means more variation. You can only compare similar data sets, though. If you're measuring weights of caterpillars and salaries of CEOs, those aren't the same data set. You cannot compare those data sets, right? But you can compare football player heights to other football player heights, right? So larger standard deviation means more variation. The data's more spread out if the number's bigger. The standard deviation is not resistant. Outliers actually have a pretty powerful effect on standard deviation. Not as much as on range. Range obviously gets more affected by outliers, but outliers still affect our standard deviation a little bit. So make sure you're aware that outliers can affect your standard deviation. It's not resistant, right? Next, the units of standard deviation. When you put units on your answer, the units of standard deviation match the units on the data. The units of the data. So for example, if you were measuring heights of football players in centimeters, the standard deviation would be measured in centimeters. The units match. The units match with standard deviation. If you're measuring money, measuring dollars, the standard deviation would be measured in dollars as well. You match the units. And then the last property is actually going to be something we've already mentioned. But remember, the standard deviation compares the variation of the data from the mean. Data from the mean. The standard deviation compares the variation of the data from the mean. It shows us how far away from the mean is our data spread out. Is it clustered or is it spread out? If you have a small standard deviation, you can expect it to be clustered around the mean. If you have a large standard deviation, expect it to be more spread out, right? You have a bigger spread. There's more variation. But it's always comparing variation of the data from the mean. The mean is the reference point. The average is the reference point. Keep that in mind. That will be important in the next chapter, the next section, 3.3. So keep that in the back of your head, right? Now, let's talk about the technique. This formula is a little messy, so we're actually going to have a technique to solve it. The technique is with this table. We're going to make this table. And the table we make has 3 headers on it. It has 3 headers. The first header is x. The second header is x minus x bar. Or, if you're talking about population, you would put x minus mu, right? You would use mu instead of x bar because you are using the Greek symbols. And then the last header is x minus x bar in parentheses with a squared, which once again, if you're dealing with a population question, you would put x minus mu with a parentheses squared. So we can see that we're going to be making a table, and we want to fill this table out. So we use the table. Step 1, complete table. So we fill in our table. Step 2 is total the last column. Step 2 is you add up the last column. Step 3, you divide by n minus 1 or big N. Step 3 is where we deal with this division portion. We divide by the n minus 1 or the big N. And then step 4 is take the square root. The fourth step is always take the square root, right? We always want to take the square root fourth. So we complete the table, we total the last column, so we add up all the numbers in the last column, we then divide, and then we take the square root. It's always that sequence. What better way to see how this works than with an example? So I'm going to try and keep this handy. You might want to do the same, keep your notes handy. We're going to look at our first example. Find the standard deviation. Use the exam score data from the previous data set to calculate the standard deviation. Now I need to remind myself, was that a sample or a population? Let's look, maybe we forgot. It's sample data, right? It's sample data. So I'm going to write the word sample right away. So I remember I'm working with a sample. I don't want to forget I'm working with a sample. It's always important to first determine if you're talking about a sample or a population when dealing with standard deviation. Next, I am going to create my table. I'm going to put x minus x bar and x minus x bar squared in the last column. I'm going to write my data like this. And I'm going to fill in the first column because I can. The first column, x, remember x is your data, 82, 57, 94, 73, 77, and 81. I'm going to fill in my data values. Now, for the second column, I can't do this until I know what the mean is. I need to calculate the mean. I need to calculate the average. Well, let's take a look. We got 82 plus 57 plus 94 plus 73 plus 77 plus 81 equals 464, and I divide by 6 because there was 6 pieces, right? So 464 divided by 6 gives me 77.3. 77.3. Remember, the mean is always one more decimal place than the original data. The mean will be 77.3. Always one more decimal place than the original data, right? So I round to one place because these were whole numbers. Now, to get these numbers, I'm going to take 82, my x, and subtract my average. I'm going to do 82 minus 77.3. And that's going to give me 4.7. So I'll put 4.7 in this box. Now, my next one, I'll do 57 minus 77.3. 57 minus 77.3 gives me negative 20.3. Negative 20.3. So I'm working through my subtractions. Next I do 94 minus the mean. 94 minus 77.3 is going to be equal to 16.7. So I'll put 16.7 there. 73 minus 77.3 for my fourth row is negative 4.3. Negative 4.3. Next I have 77 minus 77.3. Right, for my fifth row. Oops, 77 minus 77.3 gives me negative 0.3. Be careful when typing in. You don't want to make a typo, right? Make sure you double check. Make sure you're clear with your calculator. And then my last one will be 81 minus 77.3, which will give me 3.7. Oops, 81 minus 77.3 does give me 3.7. So I'm going to put 3.7 here. So I filled out the middle column. To get my last column, I need to square each of these numbers. Now, the good news about squaring numbers is a positive number squared is positive, and a negative number squared is also positive, right? 4.7 times 4.7 is 22.09. 22.09. 4.7 times 4.7. I'm squaring the middle column to get the last column. Now here, negative 20.3 times negative 20.3, well, it's going to be positive, right? Because negative times a negative is a positive. 20.3 squared is 412.09. In my third row, I got to square 16.7. 16.7 times 16.7 equals 278. 278.89. So I'm squaring each of these values to get the last column. 4.3, well, 4.3 squared, technically negative 4.3, but either way it's going to be positive, right, is 18.49. 0.3 squared, right, will give me 0.09. And then 3.7 in the last one will give me 13.69. So I squared these middle numbers to get these last numbers. Now, I like to write a little box here and put a little sum symbol on the bottom of my chart and put an equals. I need to total, right? I completed the table. I need to total the last column. I need to add up all these numbers. Well, 22.09 plus 412.09 plus 278.89 plus 18.49 plus 0.09 plus 13.69 is equal to 745.34. 745.34. That is the total of the last column, right? I totaled the last column. Step 3 says divide by little n minus 1 or big N. This is where I need to remember I'm using a sample again. Remember, with samples, you do little n minus 1, right? That's what's in the formula. With populations, you do big N. So for samples, I need to know what n minus 1 is equal to. Well, n is 6, right? There's 6 data values. So 6 minus 1 is equal to 5. So I'm going to do 745.34, and I'm going to divide it by 5. So 745.34 divided by 5 equals 149.068. So I've now divided. The last step is take the square root. So I'm going to take square root of 149.08, or sorry, 068, right? Make sure you copy it down, right? I skipped over the 6. This is a 6. 149.068, I'm taking the square root. That gives me, when I square root it, 12.20934. And now I'm ready to answer. Now, my standard deviation, I'm going to use the letter S, because that's standard deviation. I put a little curl on my S because my S's and 5s look kind of similar, just so I know it's an S. There's no reason for the curl other than just so I know it's an S. Equals 12, where do I round this? To 1 decimal place. It'll be 12.2. My original data had no decimals, so I'll go 1 more decimal place for my answer. Now, there were no units on the original data, so there's no units on my answer. But remember, the units would match. If these were measured in pounds, this would be measured in pounds. If these were measured in inches, this would be measured in inches, right? But since there's no units, I know I am done. My standard deviation is 12.2. Now, in a vacuum, that number does not enlighten me very much. We're going to want to use this number to help us make conclusions. And what we can do is we can use what's called the range rule of thumb. This is going to be super important. It's going to be our first application of standard deviation. So the range rule of thumb tells us we have cutoffs. There's significantly low values, insignificant values, and significantly high values. And we have a formula, mu minus 2 sigma. Well, let's write the sample formula. It'd be x bar minus 2s, right? If I replace them with the sample letters, this would be x bar, and this would be x bar plus 2s. The range rule of thumb says the cutoff for significant values is 2 standard deviations above or below the mean. So for our example here, if I do 77.3 minus 2 times the standard deviation, right? 77.3 minus 2 times 12.2. Well, you got to multiply first, right? 2 times 12.2 equals, and then I need to subtract that 24.4 from 77.3. It's going to give me 52.9. So I get a 52.9 here. And then for the upper limit, I'm going to use the formula, right? The average plus 2 standard deviations plus 2 times 12.2. Once again, we need to multiply before we add, right? We multiply before we add 2 times 12.2, and we want to add that to 77.3 equals 101.7. So this tells me something. This tells me that 52.9 and 101.7 are my cutoff numbers for significantly high or significantly low values. Nobody got a significantly high score because no one got better than a 101.7, right? All of my data is less than that. Similarly, none of these numbers are significantly low because they're all bigger than 52.9. So none of my grades were statistically significant. The range rule of thumb helps us spread out significantly high and significantly low values. It helps us calculate these values. We will see this several times in our course. We will talk about the range rule of thumb several times. So you will be seeing this again later in our course. But for right now, we want to introduce it because it relates to standard deviation. Now, next we have our estimation formula for standard deviation. Sometimes questions might ask you to estimate the standard deviation. The formula to estimate is S equals range over 4. And technically it's not equals, we have curly equals, it's about, right? S is about range over 4. We can estimate the standard deviation by taking the range and dividing by 4. It's an estimate though, it will not be the correct answer, it's just estimating. Sometimes you might want to make a quick conclusion about a data set and you might want to estimate. You might want to make an estimate, right? And you can do that with standard deviation, you can estimate it. Now, let's look here. It says, use the exam score data from earlier to calculate the values that separate the significantly high and low values from the non-significant values. Well, this is where I need to use that range rule of thumb, right? Use the exam score data to significantly high and low values from non-significant. So I'm going to write out what we calculated back here in words now. We want to actually interpret these values. Well, let's write significantly low exam scores would be a score of 52.9 or less. 52.9 or less, right? That was the cutoff for significantly low when I calculated it, right? So I'll use that number in my interpretation. Significantly high values, significantly high exam scores would be a score of 101.7, right? That's the number we calculated earlier, or better, or greater. And then non-significant values would be between those numbers. So non-significant scores are, I'm going to abbreviate between BTW, right? Between 52.9 and 101.7. So I can interpret those values. So I can determine whether a score is significantly low, significantly high, or non-significant. And this is where we might start to see maybe a student, let's say I'm a elementary school teacher, and I have a student who gets a significantly high score on an exam. That might mean they're not feeling challenged in the class. That might mean I need to address or provide them with more engaging materials, right? And on the flip side, maybe I have a student who got a significantly low exam. That might be a student I want to take some extra attention and make sure that they are getting caught up on the material, right? These can help me identify the areas that I want to focus on more intently. Because the scores in the middle are the non-significant scores, right? We can see significantly low and significantly high exams. So we can break things down, right? Now, our next example. Use the estimation formula to estimate the standard deviation here. So S is approximately the range over 4, which the range, remember, you take the max minus the min. 94 is the biggest, 57 is the smallest. We already calculated the range, but it's good to see it again, which gives us 37, right? This was 37, 94 minus 57 over 4, which we then can divide. 37 divided by 4 gives me 9.25. So the range, or the standard deviation, is approximately 9.25. What was it really? It was really 12.2. Kind of close, right? My estimation is pretty close, right? It's off by about 3, but it's fairly close, right? I can see the estimation formula isn't exact, but it's kind of close. Now, next, we have the variance. Variance. Small typo, probably autocorrect. Variance. The variance. The variance in an equation is the square of the standard deviation. The variance is the square of the standard deviation. The variance is the square of the standard deviation. It's directly related to the standard deviation. The symbol we use is either S squared or sigma squared. It's the square, so I put a square symbol on it, right? S squared or sigma squared. Sample population. It's got some properties. It's got a few properties. The first is it's not resistant. Once again, outliers affect it. So be aware of outliers. Outliers can have effects on your data, right? Sometimes outliers might affect us, and we want to make sure we have that in our information. And the second portion is the units are the square of the original data units. For example, if your data was measuring feet, then your variance would be feet squared. If your data was measuring people, then your variance would be people squared. Now I know square feet. That's area, right? Square feet. The area on my whiteboard is square feet. What the hell is a people squared? That unit doesn't necessarily make sense, but it's still the unit we put on the answer. The units are always the square of the original data units, even if it doesn't necessarily make sense. People squared feet squared makes sense, right? Feet squared, we have area. We know how area works, right? People squared, that doesn't make sense, right? But we still do it. That's how the units are matched, right? We want to make sure our units are correct. So let's take a look here at our example. This says use the previous data to calculate the variance. It's important to remember the standard deviation was 12.2 earlier, right? We already calculated the standard deviation of this data. You need the standard deviation first before you can calculate your variance. Well, Now I need to do 12.2 squared. Well, 12.2 squared, 12.2 times 12.2 gives me 148.84, which means my answer, my variance, which has the symbol s squared, is equal to 148.8. I have to round because it's a measure of variation. Round to one decimal place, just like you did for standard deviation. You have to round. So I get my answer is 148.8. That is my variance. Now, there were no units, so I don't have to put units on my answer here. Now, we've kind of flirted with the issue so far, but let's take a look at yn versus n minus 1. And without getting too far into the weeds, this is kind of a more complicated idea than our course is required to answer. This requires a deeper understanding of probability than we will be doing. But we divide by n minus 1, or n, because of something called degrees of freedom. We divide by those different values because of degrees of freedom. Now, I like to think of an example. If I had a box with a sample of 30 candy bars, and I wanted to choose the candy bars out of that box, when I pick my first candy bar, I got 30 choices, right? When I pick my second candy bar, I got 29. When I'm down to just one candy bar left in the box, do I have a choice for that last candy bar? No, I'm stuck with what's in the box. The last choice doesn't matter. I made one less choice than the number of candy bars that were in the box, right? Whatever's left is left over. But if I had a population of every single candy bar, the choices are not constrained by the size of the population, or the sample, right? And that's why we care. Mostly, the important thing for you guys is to understand that n is for populations, and n minus 1 is for samples, right? Make sure you understand that's the only difference in the standard deviation, right? If we go back to our standard deviation technique, the only difference is when you divide. If you're doing a sample, you divide by n minus 1. If you're doing a population, you divide by the whole n. That's the only difference between the formulas, right? And what letters you're using, because we use Greek letters or English letters appropriately, right? So make sure you know that difference. I am not going to quiz or test you on why. I just expect you to know that it is true, that you do have a difference. I'm not going to ask you about degrees of freedom, because that's a little beyond our scope of our course. But people always ask why, so I like to address why here. Now, the empirical rule. This is just like the range rule of thumb, and what it says is in a normal distribution, so we've got a normal distribution, right? It's a bell shape, right? It's normal. We can know 68% of our data is plus or minus 1 standard deviation from the mean. 95% of our data is plus or minus 2 standard deviations from the mean, and 99.7% of our data is plus or minus 3 standard deviations from the mean. When we get to Chapter 6, we will be revisiting this idea. Right now, we know that a certain amount of data will fall between scores. We know that most of the data, 95% of it, is in between plus or minus 2 standard deviations. That's a property of the normal distribution. When we get to Chapter 6, we'll be using ideas like this to represent how much data is above, below, or in between different data values if we have a normal curve. If we have a normal distribution, we can calculate things about it. I like to introduce the empirical rule here because it's another property of standard deviation. It's another use we can see, that data can be organized via the standard deviation. You know how much data falls in that gap. So if I had 100 students, and I know these two numbers, the mean minus 1 standard deviation and the mean plus 1 standard deviation, I know 68% of my 100 students have scores between these two values. So 68 of my students are in between those two values. 95% of my students will be in between plus or minus 2. I can look at the data and determine how many students fall in a given range. That works for normal curves. The empirical rule works for normal curves. It does not work for any other curves, only normal curves. Doesn't work for uniform, skewed left, skewed right, none of those, only normal. So we have an empirical rule, right? It's just another relationship between the mean and the standard deviation. Now, let's take a look at this example. Let's take a look at this next definition. Coefficient of variation. The abbreviation is CV. The coefficient of variation is the ratio between the standard dev, the standard deviation, I abbreviated standard deviation, and the mean. It's a percentage. The coefficient of variation is a percentage. It's a ratio. We express that ratio as a percentage. The formula is CV is equal to S, the standard deviation, over X bar. I divide it out, and then I need to make it a percent. So we'll multiply by 100%, right? We'll multiply by 100 to make it a percent. Or CV equals sigma over mu times 100%. Same formula, just English versus Greek letters, right? Samples versus populations. The formula is not different, though. It's the same formula. Just I want to make sure that I have one for samples and one for populations, right? Now, rounding. How do you round the CV? We round to 1 decimal. For example, maybe you get 14.8%, right? You round to 1 decimal place, 1 decimal place. That's how we round the CV. We round to 1 decimal place. The CV has its own rounding rules. Because it's a ratio, we can round it specifically. Now, we have our exam score data. Our exam score data. Let's remind ourselves that the mean for our exam score data was 77.3, and our standard deviation was 12.2. So let's calculate the CV. The CV is equal to 12.2 divided by 77.3 times 100%. So I'm going to plug that into my calculator and see what I get. Let's see, 12.2 divided by 77.3 times 100 gives me 15.78266. So my answer will be 15.8. I round to 1 decimal, and it's a percent. So my CV for my exam data is 15.8%. So I can calculate a coefficient of variation, the ratio between the standard deviation and the mean. The CV is a very powerful tool because it gives us a nice ratio between two values we already know and are important, right? Finding averages and standard deviations are super important. It's nice to have a value that relates them. Now, generally, you'll be asked to find the CV, the standard deviation, the variance, and possibly the range all within the same question. Because a lot of times in statistics, you're given a data set and you want to calculate everything you know about that data set. So let's look at our last example for the day. We have Dr. Herzog is studying height. He measures the heights of a sample. Boom, right there, sample. I immediately know everything is a sample. I want to make sure I know it's a sample. Always good to identify sample or population as soon as you can. 5 people in it. The data is listed below. All measurements in inches. I have units, inches. For his data, calculate the standard dev, the variance, and the CV. Well, the first thing I need to do is make myself a table. And I'm going to be careful to make sure I'm filling the table out with the sample symbols, right? So I make myself that same table. I put x, x minus the average, x minus x bar, and then x minus x bar squared. X is my data. I've got 64, 65, 67, 70, and 72 as my data. Now, before I can calculate the middle column, I need to know the average. I need to know the mean, right? Well, 64 plus 65 plus 67 plus 70 plus 72 is equal to 338 divided by 5, right? There were 5 data points, so I divide by 5 to get my average. Divide by 5 gives me 67.6, which is kind of awesome because it's already rounded correctly, right? I wanted 1 decimal place because my original data was whole numbers. I always go 1 more decimal place than the original data, right? So 67.6 will work. Now, I need to fill in my table. I take x, which is 64, and subtract 67.6, which gives me negative 3.6. Next, I do 65 minus 67.6, which gives me negative 2.6. Next, I'll do 67 minus 67.6, which gives me negative 0.6. And then I'll do 70 minus 67.6, which gives me 2.4. And then lastly, I'll do 72 minus 67.6, which gives me 4.4. So, I get my middle column by subtracting. Next, I need to calculate my last column by squaring, right? Remember, negative numbers squared are positive numbers, so 3.6 times 3.6. I'm squaring it, gives me 1296, 12.96. 2.6 squared, I think it'll be about 676. Hey, 676, cool. 6.76. 0.6 squared, it'll be 0.36. Yep, always good to double check with the calculator first, though. 3.6. I think this one will be 5.76. Let's see, 2.4 squared, 2.4 squared, 5.76, right? 5.76. And then lastly, 4.4 times 4.4. Oops. 4.4 times 4.4 equals 19.36. 19.36, right? I'm squaring the middle numbers to get the last numbers. Now, I always like to put a little box here and signify I'm totaling everything up with the sum symbol. Let's add these up. 12.96 plus 6.76 plus 0.36 plus 5.76 plus 19.36 is equal to 45.2. So I'll put 45.2 here. So I've totaled my numbers. Remember, after totaling your numbers, the next step is I've totaled the last column. I need to divide by n minus 1 or n. Which case am I in? I'm in a sample, so I need to know n minus 1. n minus 1. Let's see, my sample has 5 people. 5 minus 1 is 4. So I'll take 45.2 and divide it by 4. 45.2 divided by 4, right? I got to divide by 4. Gives me 11.3. And then I will square root 11.3 to get my answer, right? I need to square root 11.3. Square root gives me 3.3615472, right? When I square root, I get 3.3615472. So when I write my answer for my standard deviation, the standard deviation is equal to 3.4. Why 0.4? Why 1 decimal place? That's the rounding rule, right? My data was whole numbers. I carry 1 extra decimal place in my answers. And the units will be inches, because standard deviation has the same inches. Now, I'm not quite done yet. I calculated the standard deviation. That is 90% of the heavy lifting. I have done almost all of the work for this problem. Now, I need s squared and the CV. I have 2 other numbers I want to calculate, right? Well, s is 3.4, so 3.4 squared. Let's see, 3.4 times 3.4 is 11.56, right? Squaring 3.4 gives me 11.56. So my variance will be 11.6, 1 decimal place. Variance is 1 decimal place as well, for the same rounding rule as standard deviation. The units, however, are inches squared. Remember, variance has different units. So I got the standard deviation and the variance. Now I need the CV. Remember the CV, look up the formula right up here, is S, 3.4 over 67.6 times 100%, right? 3.4 over 67.6 times 100%. Let's type that in. 3.4 divided by 67.6 equals times 100 gives me 5.02958. I round it to 1 decimal place, would be 5.0%, right? The 2 tells me to leave the 0 alone. And these 3 values would be my standard deviation, my variance, and my CV. So the data isn't very spread. Notice the CV is fairly low. There's a very small ratio between the standard deviation and the mean. And if we look, these are pretty clumped together, aren't they? They only range from 64 to 72. They only have a difference of 8 between the min and the max. That's okay. Sometimes data isn't spread out, right? This data here was more spread out, right? The numbers were more varied. They range from 57 to 94, right? So we can see that as our data clumps together, we see the numbers decrease, right? We see the measures of variation get smaller. That should make sense, right? They're measuring the variation. The smaller they are, the less varied our data set would be. Now, unfortunately, since this is exam score data and this is height data, I can't directly compare their standard deviations, right? I'm measuring different things. I can't directly compare them. But I can understand that the numbers themselves have certain relationships, right? I can't, say that these sets are comparable because one's exam score, one's height, right? Those aren't necessarily related. But the numeric values, we can understand the properties at play, right? And that is the end of section 3.2. We have reached the beginning. I thank you all for joining me, and I will see you next time.